Okay, so everybody okay with that so far? I have an initial vorticity. I have my space and time defined. I'm pretty much ready to go and go solve this thing. The only thing I need now, if you look at this right-hand side formulation, if we have the lights up here real quick, when I go solve for the stream function, I'm going to need these kx's, ky's. And I'm also going to need it here. In fact, notice everything comes up in terms of kx squared plus ky squared. Kx squared plus ky squared. So I'm going to need not kx or ky, but the square of both. Yeah?
Should be switched in there. Up there. Yeah.
Here?
Up there. Shouldn't it be psi is equal to omega divided by that business?
Oh. Yes, if you want to be technical. That is a rare form of dyslexia that you saw there. Thank you. All right. So kx squared plus ky squared. That's the only thing I need. If I have that, everything else seems to follow. So let's go define those, and we'll go from there. Okay. So we'll come back up here, and we say, okay, now I need my kx and ky. So let's just define what the k is. Remember, I want a square, so it's 2 pi over L. This is just basically a scaling factor, just to say, well, look, you're working on a 2 pi periodic domain. FFT believes in its heart it's working on a 2 pi periodic domain. So there you go. Rescale it so it's 2 pi. Then you go from 0 to n over 2 minus 1, and then minus n over 2 to negative 1. And remember, this is all set up simply to handle the fact that you have a shift. The FFT shifts things, so we built the k to represent that shift. So I have my k values. Now this is the same k in both the x and the y direction. So I could call this kx, and then ky would look like kx. And then, but I have to make these two-dimensional as well. So not a big deal. Let's put these guys together, and then we'll mesh grid this as well. So kx, ky is equal to mesh grid kx, ky. I now have the kx and ky with the sense of directionality. And the only thing I really need is kx squared plus ky squared. So let's make a big matrix K, which is kx squared plus ky squared. That's what I want to carry around. One last piece to this, which is I'm going to be dividing by that quantity. And you know what? When kx is the first component, ky is the first component, they're both 0. So I'm going to have a divide by 0 problem if I don't take care of it. So remember, the way we took care of that problem was just to say, how about this? Instead of it being 0, make it 10 to the minus 6. Ah.
Why is it you don't just change the k11? So you're only changing one value as opposed to changing
ky2?
all the different values? Right, in this case,
So I'm only changing. Yeah, for here, all I'm doing is, so this thing, I'm only changing one component of the vector, the one that's the problem. And by the way, I'm doing it symmetrically with y, so kx and ky, so I don't have a preferential treatment. Like, for instance, I could, in fact, I don't have to change ky. I mean, as long as just one of them is not 0, I'm fine. But I'll just change both of them the same.
I guess
Mesh.
Why don't you take, once you've made your mesh, capital K, why don't you just change k11?
Yeah, you could do that too. Doesn't matter. Doesn't matter so much. Yes, you could do that. Either way, you just have to figure out the way you want to handle the divide by 0. Normally, part of the reason you do it this way is, so in some sense there, you're going like, okay, I know it's going to be two-dimensional, so I'll go change it once I get it to be two-dimensional. Here, you're just saying, this is generic, regardless if it's 1D, 2D, 3D. I've taken out the problem point, regardless of dimensionality. Okay? So in some sense, it's a little... yes, you're changing, let's say, more components. On the other hand, you're kind of setting up a more arbitrary way to just handle any dimension, right? Because you've done all your work up here, administrative work. You've done it once. And you don't have to keep track here. It's like, how many dimensions am I in? How many of these things are 0? You don't even have to ask that question anymore. Okay? All right. So we have initial conditions. We have the kx, ky, and we're pretty much ready to call the solution. So let's get out from here. Now, by the way, we're not quite ready. If you look at this thing, here's what's something important. We are solving this in the Fourier domain. So I have to say, okay, so Wt will be the Fourier domain as FFT2 of W. Not only am I solving this in the Fourier domain, I also have to send it in as a vector. So once I get it here, let's call it Wt2 will just be the reshape of this thing, Wt, into an n squared by 1 vector. That is what I'm sending in. Giant vector of vorticity. So I've Fourier transformed it, reshaped it, it's ready to go. So now when you're here, what I'm actually going to get out is not here when I'm saying W sol, it's like that's the vorticity solution. I'm really getting out the transform of it stacked up as a vector. So let's call it Wt2 sol. Because when I get this thing out, I'm going to have to, first thing I'm going to have to do is, pull out these vectors, reshape them, inverse Fourier transform before I can do anything. Okay? And this is equal to OD45. Let's call it OD45. Let's call some right-hand side function. We'll call it W RHS. So that will be our right-hand side function that we want. Call it W vort for vorticity right-hand side. I send in my time span. I send in my initial condition. I'm not going to change anything with the tolerances, so I just do that. And now I send in parameters I need. I need that mu. I need that k. I'm going to be reshaping things on the right-hand side, so I better send in my n as well. Anybody notice anything else in there? Care package of some sort? No? Okay. All right. Let's go with that for now. We can always come back and edit more. Okay, file, new file. Oop. What? Yeah, new file, right? What does it want me to do now? AppleScript file, sure. I hope that's right. No, I don't want that name. What do I call it? WVort? No, I don't want AppleScript. Cancel. All right, file. See the problem with this is? Text file, yeah, let's do that. And a location? This is so amateur. All right. Hold on. You know what's going to be easier to do? This is going to be so amateur, but that's fine. I don't even know what that is talking about. What's that? You think so? Oh! Hold on. Can I just do open? No. No, VI, come on. Now you're talking trash. I know, I broke the computer, I know, and I'm going to forever pay for it. Like, it's just so bad. Like, this is so stupid. Okay, let me see if I can find it. I'll just take a file. Let's take this allen.m, and we'll open it. Oh, file open with, and then we're just going to change it. I don't even care what's in there. All right, good. See, this is, okay, I know, it's super stupid, right? And, okay, here we go, function. We're going to produce the right-hand side, which is W vort RHS. Okay, and then we'll do a file save as. File save as. And it's going to be called W vort.rhs.m. Yes, save. Dang it. Stupid me. All right. Now, what are we sending in here? We're sending in the time. We are also sending in our initial condition, W2, WT2. Is that what I called it? Yeah, WT2. Then tolerance settings, which I'm not going to do anything with. And then we sent in, here we sent in mu kn. Mu kn. There we go. Now, let's build on this side for a minute. We're going to do all the right-hand side dynamics here. But before we do that, let's come back out here and finish this off. Which is, once I get this thing solved, we're going to build that right-hand side. It's going to carry all the dynamics for us. So we're going to get out our solution. And now let's go ahead and build something here that's going to plot it. Okay? Let's make a loop. Get everything together. Plot this thing up. And so here we go. What we have to do in this, first of all, is take our data, reshape it back, inverse Fourier transform, then I'll have my true vorticity. Okay? So, here's what we do. For j equals 1 to length of t, I'm going to go through all those values of the time that I have. And what I got to do is I got to take this function, and I'm going to go to the jth row of it. Right? So each row is a certain time. So I start with time 1, time 2, time 3. I go to the jth row, grab everything that's in that jth row. I'm going to take this thing, and I'm going to first reshape it. I'm going to shape it into a n by n. And then once I reshape it, it's ready to be inverse Fourier transformed. By the way, this should be a real function. However, I'm going to get numerical round off, right, from that 10 to the minus 16th imaginary stuff. So let's just, shave that off. Take the real part. And I'm going to call that my solution. W sol now. And this is going to be, actually, let's call it just W. And what I'm going to do is going to say, P color that. X, Y, W. Shading interp. Pause. 0.2. And it's always good to say a draw now command. The draw now, here's what one thing you'll notice with MATLAB sometimes. You'll set the thing running and you have a plot command and then it's in a loop. And sometimes it just starts running and then it says, hey, you know what? How about if I just run everything first and then I'll plot it later? So by the time it plot, it just leaves this big blank box and it's going like, I'm computing, I'm not going to plot now. It's a waste of my time. The draw now says, no, it's not a waste of your time. I really would like to see a plot now. The draw now says, stop what you're doing. Give me some love up on the screen. Okay? So that's what this does. So it's kind of important because what happens is this thing will just keep running stuff on the buffer and it'll go like, yeah, okay, I'll take care of sending stuff out to the screen later. So that will take care of that. So this is our solution. Boom. And I'm going to pause for 0.2 seconds. You're going to see a slice. 0.2. You're going to see this cool vortex rotation. Okay? All right.